Dear ladies and gentlemen, my name is Thomas Riedle and I am representing Team BRG APP Innsbruck at this AYPT. I'm going to be presenting our solutions for problem number 15, Rebounding Capsule. So the problem statement was the following. A spherical ball dropped onto a hard surface will never rebound to the release height even if it has an initial spin. A capsule-shaped object, i.e. Tic-Tac Mint, on the other hand may exceed the initial height. Investigate this phenomenon. So here you can see the phenomenon in action. This presentation consists of three main points. First the qualitative analysis, then the quantitative analysis, and then our experiments. For the qualitative analysis, I'm first going to explain how the phenomenon works, and then talk about the relevant parameters. For the quantitative analysis, we made a physical theory of an impact, and then simulated it using Python. Finally, we improved the simulation by also considering the friction during an impact. For the experimental part, we made high FPS videos of falling capsules in order to analyze them and then compare them to our theory. Then I'm going to present our error analysis. Before I can start explaining how the phenomenon works, I first have to declare how we defined a capsule-shaped object. We define it as a cylinder with two hemispheres attached to both of its ends. And because of issues with 3D printing, we had to make the capsules hollow. And for the rest of this presentation, I'm going to refer to this length as the inner radius, to this length as the outer radius, and to this as the length of a capsule. And here you can see some of our 3D printed capsules. So why does this phenomenon work? When the capsule hits the ground, there are a force and a torque acting on the end which hit the ground. The force lets the capsule bounce off the ground and the torque causes it to rotate. Now when it hits the ground again, there are again a force and a torque, but they are now acting on the under end of the capsule, so it unspins and bounces off higher than before. This is because of the conservation of energy, which means that the total energy in the system is constant. During an impact, some of the capsule's energy is transformed into kinetic and some into rotational energy. And because the total energy is constant, the faster the capsule rotates, the lower it bounces off the ground. So, during the whole process of falling, spinning and rebouncing, the capsule's energy oscillates between kinetic, potential and rotational energy. And the conservation of energy also implies that the capsule may only rebound higher than its release height if it has an initial spin. There are a few different relevant parameters for this phenomenon. Some of them are capsule specific, like the length, the inner and outer radii and the mass. Some of them are impact specific, like the impact angle of the capsule, the angular velocity and the velocity x and y. And some we didn't consider, like air friction during the falling and the material of the capsule and the ground. The impact angle of a capsule can be calculated two different ways. The straightforward but faulty way would simply be the angle between this line going through the capsule and the x-axis. However, this representation of the impact angle isn't really correct. An improved way is to consider the angle between a line going through the impact point and the center of mass and the x-axis. This angle can be calculated using trigonometry because we know that this length is half the length of the capsule minus the outer radius, and this length is the outer radius of the capsule. Additionally, we know one angle of this triangle, which is enough to calculate the impact angle. Now, let's consider this triangle in detail. As I said, this length, I'll call it b, is exactly half the length of the capsule minus the outer radius, and the length c is the outer radius of the capsule. Now if phi, the impact angle, is smaller than 90 degrees, the angle alpha is phi plus 90 degrees, and we can calculate beta with the law of cosines, and get that the improved impact angle is 90 degrees minus beta. If the impact angle is greater than 90 degrees, everything stays the same except that alpha is now 270 degrees minus phi, and the improved impact angle is now beta plus 90 degrees. Now, let's move on to the moment of inertia of a capsule. First, we'll consider the moment of inertia of a solid capsule, and then the moment of inertia of a hollow one. The total moment of inertia of a solid capsule is the sum of 2 times the moment of inertia of a shifted hemisphere plus the moment of inertia of a cylinder. The moment of inertia of a cylinder rotating about the y-axis can be found in literature and can be calculated using this formula. The moment of inertia of a hemisphere is exactly half the moment of inertia of a sphere, but in our case we had to make use of the Steiner theorem because the hemispheres are shifted towards the left and right of the capsule. And as the Steiner theorem only shifts the center of mass of an object, we had to increment the shift by the center of mass of a hemisphere in order to get the correct momentum of inertia. The total moment of inertia is the moment of inertia of the inner capsule made of air plus the moment of inertia of a hollow cylinder plus 2 times the moment of inertia of a shifted hollow hemisphere. The moment of inertia of a hollow cylinder is equal to the moment of inertia of the bigger cylinder minus the moment of inertia of the smaller cylinder, where the smaller cylinder has the density the bigger one has, as the graph suggests. The moment of inertia of the shifted hollow hemisphere can again be calculated using the Steiner theorem, but this time incrementing the shift by the center of mass of a hollow hemisphere. When the capsule hits the ground, there is a force parallel to the y-axis acting on one of its ends. Using the principle of conservation of angular momentum, we were able to derive 2 formulas for the change of the velocity and the angular velocity depending on the mass, the length, the moment of inertia, and the impact angle of the capsule. By also using the principle of conservation of energy, we get another equation, and we can solve the system by substituting one equation into another. Then we get a quadratic equation with this part being a, this part being b, and c being 0. Then we can solve it with the quadratic equation formula, and because c is 0, we can simplify it and get that the change of velocity is exactly minus b divided by a. Therefore, we get that the change of velocity is exactly this formula. The Python simulation in which we embedded these formulas works by using a small time step and updating values accordingly. So every time step, the y-velocity, the position, and the angle get updated. And every time the capsule touches the ground, we calculate the new velocity and angular velocity with our new equations. And this is a simulation in action. In our old model, there was no friction, so the force vector was parallel to the y-axis. Therefore, the capsule didn't move along the x-axis. And in our new model, we assume that the friction is infinitely large, so the capsule doesn't move horizontally during the impact. But now movement along the x-axis is possible. The new simulation works by calculating the angle at which the force acts on the capsule. With the new equation system, we got this formula. And if the angle at which the force acts on the capsule is greater than a defined freeze angle, for example 45 degrees, the angle is set back to the freeze angle, as we can't assume infinitely large friction anymore. And this is a simulation in action. So here you can see our experimental setup. We put a phone in front of a grid with a ruler on it in order to analyze the videos afterwards. We analyzed the 240 FPS videos by splitting them into single frames and then manually read out information about the capsule. Here you can see the comparison between our simulation and the reality. Every 0.004 seconds, the current position of the capsule is plotted on the graph, so you can see the trajectory. The blue dots are the simulation and the red ones the reality, and on the right you can see the capsule parameters. In the first graph, the capsule's impact angle was 55 degrees. It didn't change its x-coordinate on the first bounce in the simulation, so you can only see that it bounced less than 3 times higher than in the reality. This makes sense, because the capsule in the simulation doesn't lose any energy. In the second graph, the impact angle was 60 degrees, and both in the simulation and the reality, the capsule bounced off higher than in the graph before, because more energy is translated into kinetic energy. With an impact angle of 60 degrees, the capsule bounced off about 2 times higher in the simulation than in reality. The reason it is very hard to predict the capsule's movement is that an impact is chaotic, which means that very small parameter changes achieve very different results. But some of our sources of error were that the capsule loses energy during impact and during the falling because of friction. Also, we didn't consider that the time the capsule spends on the ground isn't infinitely small. This was the reason why it got an x velocity even if it had no initial spin. All in all, in our presentation, we gave a detailed explanation of the stated phenomenon and worked out a complex theory and simulation. Additionally, we made relevant experiments and then compared them with our theory. Thank you for your attention, and I hope to have a great discussion with you.